start. So, good afternoon, everyone. I'm Mojgan Sami, second year PhD student of from University of West of England, UW Bristol, and I'm currently gaining experience through doing an internship at ECO Homelink company. And today I'm here to present the time to lose 1 degree Celsius algorithm, or TTL, which company is using in the platform as a heat loss risk metrics. First, I'm going to give a short introduction of the company. ECO Homelink is at the forefront of home safety, offering smart solutions that help social housing providers to tackle with challenges like indoor air quality, energy efficiency, and heat loss risk. In the company, we are offering environmental sensors which measure things like CO2, humidity, and temperature, fire and CO alarms that meet the UK safety standards, and Homelink platform, or it's a dashboard that delivers real-time insights. There is also an application that lets residents to keep track of their home's health. But what's next? We're working on smart meter integration, technology-enabled care, radon sensors, and wet heating system monitors that add even more value to the platforms. With 470,000 connected devices and 69,000 environmental sensors, growing 230% in the last year, the company is driving significant improvement in the housing management. These devices are connected through 68,000 gateways, and on a daily basis, these devices are capturing 16 million readings, which using in the dashboard, and through analysis, 93 million insights calculates, which leads to raising 1.8 million alerts to help address the potential issues. In real time. Okay. What is TTL algorithm? The TTL algorithm uses the physics-based model relying on Newton's law of cooling. It uses nonlinear regression to match the temperature changes in the model, and it uses linear regression to figure out the average temperature of each room, considering the temperature outside and the temperature of nearby rooms. Sudden temperature changes, like when windows are opened, are detected and removed through Z-score methods to keep the data more validated. There are different factors influencing the TTL, like different building types, property types, room characteristics, passive and non-passive house buildings, and I compared a few of them with the last year's data. I compared the performance of different attachments, detached, semi-detached, entrance, and mid-terrace of buildings across different seasons in the last year data, and the data reveals an unexpected performance patterns where detached homes outperform connected properties by up to 20 to 30% performance gap, despite having greater external wall exposure. These findings suggest that construction materials and standards likely have more impact than shared walls on heat retention. Different property types like cottages, bungalows, tower blocks, houses, and flats were compared across different seasons. Data reveals vertical properties like tower blocks and flats outperform ground level properties by up to 2 times longer heat retention. And in this finding also suggests that vertical properties, the start performance gap suggests that heat stack effects and shared ceilings or floor thermal mass may likely play a crucial role in energy efficiency. There's also significant geographical variation in different parts of the country, with northern cities outperform coastal locations despite having colder climates. Southern and or central cities demonstrate remarkable stability across different seasons, and there's up to 200 minutes performance gap between the best and the worst cities, and you can see the average TTL values for UK cities in the last year. I also compared the different room types like living room, kitchen, bedroom, and bathroom across different months, which shows that bedrooms consistently showing the highest retention times, and kitchen has the lowest one, but it's the most stable one. Also in summer months, we have the peak heat retention across all rooms, and in winter, we have the most consistent retention times across all the rooms. Next one, I compared the EPC ratings. There's a huge misalignment between EPC ratings with heat retention capabilities. 72% of band B properties are in the lowest or the worst TTL range. This is something that can be expected for band D, but not for band B. And so it means higher EPC ratings don't correlate with better heat retention, and also the EPC ratings, the EPC assessment may not fully capture the whole building's thermal performance. Through these charts, we compared the thermal performance of passive and non-passive house buildings. Generally, passive house buildings perform better. They can retain heat 60% longer on average, and we have the same patterns for across all different room types, with bedrooms having the most differences. And again, the same patterns can be seen on different seasons. So, for example, passive house buildings in winters have the average TTL values for passive house building in winter is like 160 minutes, but for non-passive house building it's 100 minutes, which is like 60 minutes differences, and implies better energy efficiency and comfort in passive house design. Yeah, almost finished. And we compared different risks. I chose only 3 of them for passive and non-passive house buildings. And again, passive house design show lower risk across all categories. And passive house only have like slightly lower risk in air quality, but for damp and mold and heat loss risk, the difference is much more significant. And so, for example, 54% lower risk in heat loss and 37% lower risk in damp and mold. We haven't compared our algorithm results with any other experimental method, but now we are working on finding HDC, like estimating HDC in the whole house, whole buildings, using AI and machine learning methods. And we are also working on collecting data set using U-value sensors and design SAP software, which is actually my thesis project. And in contribution with Annex 94, the company offers advanced sensors compatible across EU countries, alongside with dashboard access for real-time monitoring. And if algorithms or frameworks are developed, we can run them in our own data sets to assess performance. And also we are able to provide anonymous data from a limited set of buildings for integration in the Annex framework. Thank you for listening.